Hello folks, tonight we're going to be talking about partial fractions and proper integrals, and I'll do one problem with an error bound on a approximation for a definite integral. So if you have any questions, same as always, please post them in the chat box. I'll be happy to help out as best I can. Otherwise, just enjoy the show, I guess. So without further ado, I'm basically taking some problems that we're struggling with. So we want to find an appropriate partial fraction decomposition for the integral. And so we have x to the 21st minus 8x to the 14th plus 8x to the 7th minus 64 all over this x cubed minus 5x squared plus 4x cubed plus 4x, that quantity cubed. And then we have an x to the 4th minus 256, that quantity squared. So an easier way to kind of see that integral, that thing is equal to, so we have x to the 21st, all the numerator stays up there, and that won't really play a role in terms of our partial fraction decomposition. But I saw a lot of people were struggling with how this looked. So notice you have an x term in all of those, so we can factor out an x inside, and that leaves us with x squared minus 5x plus 4, and then we can cube that quantity. And then in the same regards, we can actually factor this thing. If this was just x squared minus 256, it might be a lot easier. But since it's x to the 4th, what happens is you're going to have an x squared term in both spots. And it means it's a minus and plus since there's no middle term, and these two have to be equal. So it's going to be the square root of 256. So if you actually don't know the square root of 256, that's okay. You can kind of do the math and just kind of guesstimate. You know what 10 is, that's 10 squared is going to be 100. 20 squared is going to be 400. So it's somewhere in between there, right? And the magical number, think of things that square to give you a 6, and it's going to be 16. Okay, so and we have all that quantity squared. So within here you have a couple things that break down. So this actually breaks down to x minus 4 and x minus 1, and this x squared minus 16 breaks to x minus 4, x plus 4. And sorry, I forgot the dx there. But so all of this equals the integral of, it's going to be kind of nasty now because of all the terms down below, but it'll tell us how to break this thing apart. X to the 21st minus 8x to the 14th minus, or plus 8x to the 7th, and then minus 64. And then we can go, well, notice we got to distribute that cube to each of the factors, so we'll get an x cubed, and we'll have an x minus 4, the quantity cubed. And then we'll have an x minus 1, the quantity cubed. And then in the second part, we'll have an x minus 4, the quantity squared. And then we'll have an x plus 4, the quantity squared. And then finally, last but not least, we have that x squared plus 16, the quantity squared. Alright, and we need a dx thing sitting right there. Okay, so without further ado, where do we go from here? Well, when you take a look at this factor and this factor are the same. So you have 2x minus 4s sitting there, so we can have x minus 4 the quantity cubed, and x minus 4 the quantity squared. That becomes just x minus 4 the quantity to the 5th, so you get an x cubed, and x minus 4 the quantity to the 5th, and then we have an x minus 1 the quantity cubed, and then you have an x plus 4 the quantity squared, and then you have an x squared plus 16 the quantity squared. And then on top you still have that x to the 21st minus 8x to the 14th plus 8x to the 7th minus 64, and then we can toss out a dx at the end. Okay, so what does this do? Well, if you notice, we're just concerned about the denominator. So we have an x cubed. So the way we start our partial fraction decomposition, we go a over x. But we're not done. There's another possibility. We could have something over x squared. So you go b over x squared And you could like label them A1 and then A2 and so on and so forth. There's all sorts of different ways you can label the constants. But 8 over, oops, that should be an x cubed. And then we'd be done with that part. Let's see, we might get the whole alphabet. I'm pretty gosh darn close, so we'll have 8, 11, 13. Yeah, quite a few here going on. So in this case, you keep on going. You get d over x minus 4 plus an e over x minus 4, the quantity squared, plus an f over x minus 4, the quantity cubed, plus a g over x minus 4, the quantity to the 4th, that's a 4, plus h over x minus 4, the quantity to the 5th. So we're still moving right along. We got to keep on going. We need I, j, and k for the x minus 1, trying to get up to that cube factor. So we have I over x minus 1 plus j over x minus 1, the quantity squared, plus k over x minus 1, the quantity cubed. And then we have the x to the x plus 4 terms, so we'll have L and then over x plus 4. And excuse me for having to go to the next line, but it's just a big partial fraction, so you have plus m over the quantity x plus 4 squared plus n. Now here's where it gets tricky. You have an x squared excuse me, plus 16. So it's not just n anymore. Since that's a quadratic, we have to go in nx plus, instead of o, because that looks like 0, I'm going to use p. And then finally, when we square that, so you have an x squared plus 16, the quantity squared, you have a qx plus r. All of those are possibilities. Obviously, that's a long list, but yeah, at the end of the day, that's our partial fraction decomposition. I'm not going to have you try and solve something like this. That's not my purpose or whatsoever, but if you can understand how to break this one apart, you can do any other one. And this is where you'd call for some software, some mathematical software, type in the system of equations that result from this, and then you could solve that in a matter of a few seconds. Okay, that's the big idea which you'll be building towards, but until you know what the partial fraction decomposition is, there's no use in even moving forward. So actually, when you do break this down, all the integrals are going to be pretty easy. So you're going to have a lot of natural logs. You're going to have a lot of like x to some negative 2 power I see here, and things along those lines. It's the same sort of antiderivatives over and over again. It's just a matter of getting those constants right. So set up, that's actually just algebra is all that we're doing there. So an integral that some people struggled on, I wanted to touch on real quick here. Evaluate the integral. You have ax divided by x squared minus bx. So now, taking a look at this, if you notice, the denominator has something nice in common. Can anyone tell what's in common on the denominator? What can you factor out? And you can go ahead and type it in the chat box if you're watching. So how can we factor that denominator? Okay, so notice both of those terms have an x in them. So you can go, this is x times the quantity x minus b, dx. And so this one, it says it's a partial fractions problem, but it doesn't have to be a partial fractions problem. Your x cancels out, and notice what we're left with is a over x minus b dx. Now, there's a couple ways. Some people might recognize this right away and know the answer. If not, I'm going to go through it the long way once, and then I won't cover it unless you all have questions on it. So you have a, we can pull out because that's just a constant, and we're taking our antiderivative with respect to x, so we don't have to worry about the a. So that means we can do u equal to x minus b, and that means du equals dx. So this whole thing equals a times 1 over u du, which we should recognize that is a times the antiderivative of that is natural log of the absolute value u plus c. And so this whole thing equals a times natural log of x minus b plus c. So you might say, well, Josh, this is a partial fraction section. Why didn't we use partial fractions? People get partial fraction happy, and I want to try and illustrate that, hey, you don't have to use that over and over and over again. Okay, so we can use different stuff in order to solve these problems, and that would be the easiest way. But just to illustrate how we would do one with partial fractions, I'm going to up the game a little bit. And by the way, why would we do such a thing in terms of evaluate the integral? Well, so what this does, this generalizes. So say I give you evaluate the integral, and you can go ahead and pick your favorite number. If I give you, say, pi squared x all over x squared minus, and now for b, let's do the sine of e, which is just a constant, times x. Right? So this looks all sorts of nasty. We got all this funky stuff. Pi squared sine of e. What the heck is going on here? Well, according to that previous result, what does that say? Well, notice a is just pi squared, and your b is just sine of e. So this whole thing is just pi squared natural log of x minus sine of e. And this is what we try and do oftentimes in mathematics, is find some generalization as to what's going on. That's why we do this with general constants, if we can. And you'll see that later in the improper integrals. That'll cut down a lot of time for us. So moving forward, evaluate the integral. We have ax plus c now divided by x squared minus bx. So this will be a lot harder. This is where we do actually need that partial fraction decomposition. So we'll have ax plus c, and then we'll have x times the quantity x minus b. Now this has to break up. So we'll have, not to confuse us here, but we'll have a capital A over x plus a capital B over x minus b. So notice what you can do is you can rewrite this as a times x minus b over x times x minus b plus b times x over x times x minus b. So this piece and this piece, these two meet in the middle. They have to be equal. Well, notice they all have the same denominator, so we don't have to worry about the denominator. What we get at the end of the day is ax plus c equals a times the quantity x minus b plus b times x. So taking a look at this, we can do some shortcuts, and that's what we're actually going to do. The first shortcut, the easiest one, let x equal 0. So notice you get a times 0, which is just 0, so you get c. So this is an implies symbol. So that means you get c. Oh, okay, so great question. So there's a question, how do we get rid of the denominators? You don't even need to cross multiply. So if I multiply both sides, so let me go over here, I'll go x times x minus b, and then I go x times x minus b times this whole quantity right here. Notice the x times x minus b's cancel, so there goes the x, and there goes the x times, or the x minus b, and then I have to distribute this to both terms, so it goes here and it goes over here. So that means we're going to cancel this, x minus b's cancel with those x minus b's, and then the x's cancel off with those x's right there. Great question. Does that make sense then? Okay, awesome. So now, moving forward, so this is what we have. Now, we can choose x to be any value, and what we're kind of doing here, it does get tricky. Sometimes you might have to distribute this out, but since these are both linear terms, our life is a lot easier. And so, in terms of what we're looking at, we can plug in for either of the x values. Well, notice if we plug in x equals 0, it's going to take that b term away, and it'll also take this a term away. So when x equals 0, what does this give us? Well, this gives us, I'll actually write it out for one step. A times 0 plus C equals A times 0 minus B plus B times 0. Now, what's the big deal with that? Well, if you take a look, A times 0 is just 0, so you get C equals negative B times A. Now remember, I know this is tricky with all the different letters that we're looking at. We're trying to solve for A, the capital A. So solve for these two. So solve for us, right? That's what we're looking at. We want to try and get those down. So when you take a look at this, if we're solving for A, we get A equals negative C over B. So we got a constant there. We're in good shape. Now where do we go from here for the next part? Well, we'll go back to our original equation, which I just starred. Okay, so we have a star right there. Now what do we want to plug in? Well, notice on the right hand side we have an x minus b as a factor. Well, if we plug in b, that little b I should say, lowercase b, notice the a would disappear and we can solve for the uppercase b. And that's the idea. So when x equals little b, what does that mean? Well, that means we have a times little b, or little a times little b, plus c, and then we have equals a times b minus b, which is going to be 0, plus b times little b. Okay, I know this looks crazy with all those symbols, but I'm just trying to illustrate that, hey, numbers aren't necessary for a lot of these. So what we're left with is AB plus C equals, I'll just switch the order here, little b times capital B. And so what that means is that AB plus C all over little b equals uppercase B. So our integral, that tells us how this thing is going to behave. We have ax plus c, and then you have an x squared minus bx dx. Well, this is going to be the capital A. What was capital A? Well, if you recall, so we have, this is the integral of negative c over b over x dx plus an integral of, well, now it's ab plus c over b all over x minus b dx. Okay, so this looks scary at first, but then when we realize this little lowercase c's, the lowercase b's, and the lowercase a's, all that stuff's constant. So we could pull that out in front. So we get negative c over b times the integral of 1 over x dx plus, and then we have ab plus c all over b times that second integral. So I'm going to ask real quick, what is the antiderivative of 1 over x dx? And you can just type it in the chat box if you know the answer. So just the 1 over x dx, what is that antiderivative? Yeah, so that's correct, and you'll get a bonus point for that. So you got an eagle egg. So the natural log of x, that's right. And so that's just the natural log of x. So you have negative c over b, natural log of x. And then we just kind of did that other one in the previous slide. So that 1 over x minus b is just another natural log of x minus b with just that constant out in front. So you have ab plus c all over b times the natural log of x minus b. So yeah, Chelsea, just make sure to send me an email saying you got another eagle egg, so I'll give you a bonus point on that upcoming homework. Good job. All right. Hopefully that makes sense on this problem. I mean, all you have is a bunch of constants and then it's times some natural logs. So, but I can toss in any constants. I now have a solution for all of them. That's the key component to a lot of these partial fractions, if you could start to generalize. Most of the problems you encountered, though, in the homework were where there were numbers like 2, 3, 5. These gave people some just some problems there in terms of where there were some difficulties out of all the homework. So moving forward, we'll get into improper integrals. So what's the key to improper integrals? Yeah, so that's, I see a comment, it looks easier and takes way less time when you do it. Yeah, that's part of, it's just practice. I mean, I've done this, you know, someone was in my office today. It's thousands of hours. I mean, when I first did it, the first time I took Calc 2, same song and dance, there was a big struggle. It takes a lot more time. But over time, if you practice a lot of general ones, you start to get the idea. And it's just the same process over and over and over again. But it's that practice. If you practice, you can do it. It just takes a lot of practice. That's all. In this one, when we're getting to improper integrals, what does it mean to be improper? Well, it's just talking about when is this thing undefined. And so in this case, you actually have two values. You have -2. Notice if you plug that into the denominator, you get 0, and you can't divide by 0. If you plug in 2, you run into a problem. So what we do with improper integrals is we approach those numbers that are problem points, and then we try and evaluate the integral as we approach those numbers. So rather than taking two limits at once, a nicer way to kind of do this is to break it up first. We'll go from -2 to 0 of y dy. And y 0, well, it didn't have to be 0. It could have been any number between these two that would satisfy where this thing's defined. But I like 0 because it's easy to plug in at the end. So that's the only reason you see 0 being chosen. If you want to choose 1, go for it. That's fine. You're just going to have a little bit more work when it comes down to it. So that's just, I mean, doesn't have to be 0. It can be any number. But as I mentioned, we have to take limits because we can't just plug in -2, essentially. So with our limits, you can pick your favorite letter other than y in this case. So I'll do limit as t approaches -2 of the integral from t to 0, because now we're approaching that value. We don't have to worry about it anymore. So we have y dy over the square root of 4 minus y squared plus the, oops, need a limit again. And you can pick your favorite letter. Limit as q approaches, well, we want 2, and then we'll go from 0 to q of y dy over the square root of 4 minus y squared. And my claim is on a lot of these, that's a y squared too, by the way. My claim on a lot of these is not so much the struggle of the limits themselves. The struggle is the antiderivatives for a lot of people. It might not be the case for you, but a lot of the problems I see are involved with the antiderivative. And in this case, most people think, yeah, I can use trig substitution. And yes, you can, but there's a much easier way. And what I'm going to do, rather than go back to the limits right away, I'm going to actually solve an integral that's more general, just because it'll be easier for us to plug in once we figure out the antiderivative. So with this general antiderivative, we want the integral of y dy over the square root of 4 minus y squared. And as I said before, you could do a trig substitution, and it'll just take you a little bit more work. The easiest route is a u substitution. And you have some options here. There's all sorts of options. This won't be the only choice for you. I actually saw one today, as a matter of fact, on a similar problem that was a little bit different in terms of the choice. So if you choose u equal to 4 minus y squared, notice you get du equals -2y dy. Right? So what that means, if we're solving, you have a couple ways you could do it. You could try and get something that matches up above, or you can try and solve for dy and then just make that replacement. In this case, I'll actually just try and match what's in the numerator. So because notice if you go du over -2, you get that equals y dy. So I can replace the numerator now. And so this equals the square root of u in the denominator, and then we just said that's -du over 2. So we can pull that -1/2 on out. So you get -1/2 times the integral. And another way we can write this, when you have a square root of u in the denominator, that's just the same thing as u to the -1/2 du. And so now we can kind of use that power rule idea. So we have negative 1/2, and then it goes, so you add 1 and you divide by that. So it goes 1 over, when you add 1 to negative 1/2, you get positive 1/2. So 1 over 1/2, and then you have a u to that positive 1/2. And then we add c. So notice these two things right here will cancel. You're left with just negative 1. And so this becomes negative, and then a 1/2 means a square root. So square root of u, which is 4 minus y squared, plus c. Now, when I take this, so going back up top here though, so when I go negative 2 to 2 of y dy square root of 4 minus y squared, we have two different limits we're going to have to evaluate. So limit as t approaches negative 2. And then we know the antiderivative. So rather than doing all that work and changing bounds and doing all that jazz, we could just plug in negative square root of 4 minus y squared. And we drop the c because it's a definite interval. So this goes from t to 0 plus the limit as q approaches positive 2 of the same exact thing. So negative square root of 4 minus y squared evaluated from 0 to q. Okay. And so from here, we can just plug in our bounds. So you get limit as t approaches negative 2. And you get negative square root of 4 minus 0 squared, which we should be able to solve here in a second, minus negative square root of 4 minus t squared, which we also should hopefully be able to solve in a second. So you get limit as q approaches 2 in the other case, and then we get negative square root of 4 minus q squared minus a negative square root of 4 minus 0 squared. All we did was plug in the bounds. Okay. So now, hopefully I can erase the bottom piece. If not, sorry, I'm going to just need to make some space. If you need me to reproduce it, that's fine. Alright, so now that we have a little bit more space, what happens now? Well, we plug in. So this should equal, well, this goes negative square root of 4, which is negative 2, minus, well, square root of 4 minus 4 is 0, so that's just going to be 0, plus 0, and then we get minus, and then plug in here, you get negative, and then you get square root of 4, which is 2, so negative 2. And now all we need to do is just kind of simplify this. Negative 2, and then minus a negative 2, well, that makes 0. So in terms of our solution, when it goes to a point, a real number of some sort, that's not infinity or negative infinity or does not exist scenario. So this is converges to 0. That's exactly what we have there. So the main questions we're going to actually be looking for isn't so much convergent or I shouldn't say, isn't so much the point that we're going to, it's the convergent or divergent part. And this is going to show up later when we get into Module 3 talking about series and things along those lines. So hopefully that makes sense. If not, let me know. Another one that tends to trip people up is this negative infinity to positive infinity x dx. What the heck's going on here? So I'm going to try and answer that problem. Notice this one can be broken up. You pick any point that it's continuous on. It doesn't have to be 0. I just prefer 0 because it's easy to plug in. So because this thing is improper, since you cannot ever hit negative infinity or positive infinity. Okay, so we'll break it up at 0. And so what does this mean? Well, if we do that, we could now take a limit as we'll say p approaches negative infinity, and we'll go from p to 0 of x dx plus limit as, and you can pick whatever you want. I'm putting a smiley face here. Smiley face approaches positive infinity. An integral from 0 to our smiley face, okay, of x dx. And so now what happens? Well, you get the limit as p approaches infinity. The antiderivative of this is just x squared. And divided by 2, or 1/2 x squared, whichever you prefer. And this goes from p to 0 plus, we get the limit as smiley face goes to positive infinity, and then we get 1/2 x squared again, evaluated at 0, and smiley face. Okay, so now it's time to plug and chug. And we're going to have to think about this, and I'll explain what most people say and what actually happens. So you plug in 0, you get 0 minus 1/2 p squared. Okay? Oh, I'm sorry. I put p as positive infinity. That should be negative infinity right there. And in our second case, you have limit as smiley face goes to positive infinity. And this would be 1/2 smiley face squared, and then minus 0. So as p goes to negative infinity, you square this becomes positive infinity, and so you have a negative here, so this is negative infinity. And then the other part, you get 1/2 smiley face squared. That looks like it's going to positive infinity. So most people will say, oh, this cancel, and that's it. Oh, no, not quite. Here's the deal. This thing, just think about it, is part of the integral. And is this convergent for this part of the integral? Well, no. This part is divergent, right? And that's only a piece of this integral, okay? In a similar manner, well, this is just another piece of the integral. So you have another divergent part. So if you have both parts diverging, what happens? Well, that means that this thing is divergent. A lot of people think they cancel out. That's not the case, okay? So keep that in mind. You get a divergent integral just because if you have infinity, negative infinity, people think, oh, they cancel. Nope, not quite. You get two divergent parts. Each part's divergent, so this thing goes away. So that tends to be a tricky one for a lot of people to wrap their head around. The other one that's a big idea is this, when you have x to the p, we want to try and solve for tons of them at one time, because that actually finishes off a ton of integrals all at once. So yeah, so when we move forward, I'm glad the last one made a little bit more sense in terms of each part being divergent. Now notice that was the same function. If I start to do different functions, I can have some crazy stuff happen, and I can illustrate that. But since that was the same function, you can't have part of it be divergent, another part be divergent, and all of a sudden it pops out and it's convergent. No, it doesn't work like that. If just one piece is divergent and it's just a slice of that function, the whole thing's going to be divergent. And we'll discuss that more at length in just a minute. So, for what values of p does the integral, this 1 to infinity 1 over x to the p dx converge? And this is going to be a big part of what we're going to call the comparison theorem. So this is one to pay attention to. You're going to use it over and over again throughout the semester, actually. So this pops up again later on down the road. So the first thing, in order to take this, I would recommend rewriting this as x to the negative p dx. We'll figure out what the general integral looks like. So the antiderivative, you just go 1 over negative p plus 1, and then it's x to the negative p plus 1. And another way to write this is, so it goes plus c usually. So you can go 1 over 1 minus p, and notice that's not the problem. It's going to be, when we write this other part, I'm going to write it slightly different. So another way to have written x to the negative p plus 1, actually let me show the extra step. We could rewrite this as x to the negative, and then we can go p minus 1, right? And the reason why, if you distribute that negative sign, you get negative p, and then you get plus 1. So with that, though, what does that do? That means we get 1 over 1 minus p, and then you get 1 over x to the p minus 1. Okay, so that might seem kind of tricky. And there's one caveat here. I'm assuming p is not equal to 1. If that's the case, we run into a big problem if p happens to equal 1. And I'll discuss that case in just a second, because that's a whole different scenario altogether. It's the only case, though, that we have to worry about. So, I'm going to write up here, assume p does not equal 1. Right? Then what happens? Well, then this integral, 1 to infinity of 1 over x to the p dx, what do we get? Well, we get this is equal to the limit. The problem point is going to be that infinity, so we'll go limit as t approaches a positive infinity, and we get integral from 1 to t. Oops. So in terms of, will there be times when we assume otherwise? Are you talking about the assume p does not equal 1? Yeah, I'm thinking that you're referring to that. Yeah, so there's only going to be one case, and I'll explain why that's a problem. If p equals 1, and I'll do this case in a second, notice it's one slightly different case. You're left with 1 over x dx, integral from 1 to infinity. What is that antiderivative? I jumped into doing this. I should have written it ahead of time, so I had to assume this ahead of time. If p equals 1, you get 1 over x dx. We know that antiderivative is natural log of x. So it's the only case it's different. All the rest fall into this x to the negative p plus 1. So that's the only one. I was just kind of setting that up. It's not going to change our final answer. You can kind of see what's happening here. If I plugged in 1 down below, notice I get negative 1 plus 1 and 0 in the denominator. Yeah, and so the natural log, that's exactly right. So the natural log is going to be a problem as well. So I'm just tossing it to the side. I'll make sure of it a little bit later, but for right now, just we'll deal with the main chunk of the problems. And we'll talk about domain and all that stuff a little bit later in terms of like Laplace transforms and things like that. So this thing equals 1 over x to the p dx, and we just found that that antiderivative is well, we need the limit first. Limit as t approaches infinity of 1 over 1 minus p times 1 over x to the p minus 1 evaluated at 1 and t. And this thing equals, it looks all sorts of nasty, but we get 1 over 1 minus p times, since that's just a constant, I'll write it out what's going to happen here, and we'll put the limit as t approaches infinity. Okay, so we have that. We can plug in our t. 1 over t to the p minus 1 minus 1 over, well, 1 to the p minus 1 is just 1. Okay? So now, let's try and solve this thing. What the heck does this look like? So if you have this actually having the limit as t approaches infinity, we need that piece to stay in the denominator. So, with that in mind, what happens? Well, so I'll erase that bottom piece. We already had our antiderivative. We've taken care of that. So if that stays in the denominator, we're good, because we have 1 over infinity. That essentially goes to 0. Okay? So if that's going to stay in the denominator, the only way that can happen is if p minus 1 is greater than 0. So notice that means p has to be greater than 1. Okay? And then that whole thing goes to 0. So that whole piece will go to 0 in that case. So that's good. That's what we want. So what are we left with? Well, we're left with 1 over 1 minus p times negative 1. Well, we could take that negative 1 and multiply it by the denominator. So this is, if you notice, it's going to be just 1 over, you can write it as negative 1 plus p, or more simply, 1 over p minus 1. So we have a general formula for when the case is p does not equal 1. And so what we have is converges. So this integral, 1 to infinity. Now notice the x to the p is in the denominator, but it converges when p is greater than 1. And the only other business that we need to check is when p equals 1. So if p equals 1, let's see what happens. Then we get the integral from 1 to infinity of 1 over x dx because p is 1. And that equals the limit as t approaches infinity of 1 to t, the integral from 1 to t of 1 over x dx. And that means that we get the limit as t approaches infinity of the natural log of x evaluated at 1 and t. So this equals the natural limit as t approaches infinity of the natural log of t minus the natural log of 1. Just in case you don't remember, the natural log of 1 goes to 0, but this thing will go to infinity. So this equals infinity, so this diverges. So I didn't even have to worry about it. So you get your solution. This thing converges only when p is greater than 1. So what does that mean? Well, here's the easy stuff. If I take an integral from 1 to infinity of 1 over x squared dx, I know it converges since p equals 2. If I take the integral from 1 to infinity of 1 over the square root of x dx, I know it diverges since p equals 1/2, right? 1/2 is not greater than 1, so you know it's going to diverge. So I don't even have to calculate. If it's just asking me convergent or divergent, I don't even have to calculate anything. I know right away what the answer is going to be. So keep that in your back of your mind, because that's going to do a ton of stuff for us. And notice I couldn't change the 1. I could just multiply by some constant. Who cares, right? It does the same song and dance. And this is going to pop up over and over again in what's called the comparison theorem. So let's suppose that f and g are continuous functions with, we have f of x being the larger of the two. So f of x is greater than or equal to g of x. But we need both of them to be greater than or equal to 0. That's actually pretty important for some x greater than or equal to a. So there's some things that we have, and there will be some things that we don't have. And this is why I always recommend drawing the picture. So you see the picture here. This thing goes on forever and ever, right? And the same thing here. And so we're going to infinity. That's our improper integral. If you look at f of x, if we start shading this in, right, it's going to be all the way down below and up above, right? So notice it's more area than g of x. So if we know that this thing with more area than g of x is going to be convergent, meaning it goes to a number, well then what's going to happen to that integral, that improper integral involving g of x, that's also going to be convergent. Okay? So and that's because you have a larger integral being convergent, and so that smaller thing that's sandwiched in between 0 and that. Now, it gets to be a different ballgame if it's not sandwiched between 0 and the function f of x. Yeah, we can't say anything. But if it's positive, we're good. So, in the second case, though, if the smaller function, g of x, is divergent, then that improper integral from a to infinity of f of x dx is divergent as well. So notice they go together. So here's some extra bits that people make mistakes on. If the integral from a to infinity of f of x is divergent, so the larger integral is divergent, we cannot say anything about the integral from a to infinity of g of x dx. That's why I always recommend drawing yourself a picture. It's quite beneficial, because notice if f of x is larger than g of x, and we just know that larger part's divergent, that does not say anything about the smaller piece. In a similar manner, if the integral from a to infinity of g of x is convergent, then we cannot say anything about the integral from a to infinity of f of x dx, because we have the smaller part being convergent, but we could add a whole bunch more stuff to that f of x. So keep that in mind. We got to try and we're always going to make a guess when using this comparison theorem. Is it convergent, divergent? Then we got to figure out, okay, do we want to be looking for a larger function or a smaller function, depending upon our guess. Okay, so the first problem, and it kind of takes some practice getting the hang of, but if you look at number 1, what do you think? Do you think convergent or divergent? So just just toss out a guess, and we'll try and figure it out. So I just want to see, what would you guess, convergent or divergent? And then I'll kind of give a hint as to what to look for. And it doesn't always work, but it'll be beneficial in the long run. So is this thing convergent or is this thing divergent? So convergent, very good. So that's actually a real good guess right out the gate. And I'll kind of explain why. The key component that I would look for is what that x value is. And you might have stuff on top or on bottom. But so in terms of what we're looking for, that's what we're kind of focused on, is those x raised to power. It doesn't always work that way, but that's what we're mainly focused on. So now, where do we go from here? So if we're thinking this is convergent, we need to find a larger function that's convergent. Well, before we do that, let's focus on the x squared plus 5. And remember the p values that we were looking for. So in that case, you get x squared plus 5 is greater than or equal to, well, it's going to be greater than or equal to x squared. And you might say, well, wait a second, Josh, that doesn't set this integral up. We want it to be smaller. And well, the nice part is, when you take 1 over x squared plus 5, notice that just reverses. And I wrote greater than or equal to. I could actually make it strict. And I should say for x greater than or equal to 1. And notice that this is greater than or equal to 0. Right? In a similar manner, you have that this is going to be less than, I'll just put the equal just for kicks, not necessary. And then we know, since this was positive, you have an x squared plus 5, it's always going to be positive. That's important. We have that this is positive. So this thing's bounded by 1 over x squared. And notice, 1 to infinity of 1 over x squared plus 5. That would have to then be, and I have a dx here, less than or equal to 1 to infinity of 1 over x squared dx, and 1 to infinity of 1 over x squared dx is convergent. So what happens to the original integral? We have 1 to infinity. Oh, and I need to put 0 is greater than or equal to that. So 1 to infinity of 1 over x squared plus 5 is convergent by the comparison theorem. Okay, so hopefully that makes sense in terms of how you write this up and things along those lines. And notice what we did is we just we didn't even evaluate an integral. If you wanted to notice, we just talked about that integral from 1 to infinity, 1 over x squared dx. But notice this is convergent since p equals 2, right? In our previous case, we're talking about the 1 over x to the p. So we're good there. So you just relate it back to ones that we know. In a similar manner, we can rewrite this next integral from 1 to infinity. An easier way for us to write that is 1 over e to the x and then x squared. And e might scare you at first, but it's essentially 2 point something something something, right? So when we take it to the first power, you get excuse me, some number like 2, and then you take it to the second power, you're going to get some larger number larger than 4, and so on and so forth, right? But so we're just getting larger and larger. Remember, we want to make this bigger than 0, right? And that's going to be the case because we're always talking positive. So 0 is always going to be less than or equal to e to the x squared. And in this case, we can even say that. So now what we want to do is compare it to something else that we might be able to know how the series behaves. So if you take e to the x squared, notice that e to the x, remember that starts off at 2 and just gets larger. So this is bigger than x squared again. And in a similar manner, what we get is then 1 over e to the x squared. It's larger than 0, and it's less than or equal to 1 over x squared. Okay, so see how we're just playing with those inequalities. So now we have our inequality that's set up, and so we have that piece, we have the inequality that we're looking for, since the integral from 1 to infinity of 1 over x squared dx converges. We find the integral from 1 to infinity of 1 over e to the x squared converges by the comparison theorem. Whew. So kind of tricky at first, but hopefully getting the hang of that. Now, so those both had x squared. I want to see what happens. Now we have a square root involved. What do you think? Convergent or divergent on this one? So we have the integral from 1 to infinity, 7 plus sine x, all over the square root of x minus 0.5. What do you think? Convergent or divergent? In either case, too, also maybe make a guess as to, yeah, so divergent, that's a good guess. What function do you think then? If you think it's divergent, what function do you think we should compare it to? And that's where we're going to play the trick here. So we see a sine of x, so that looks kind of scary at first. But so yeah, divergent is right on the money. And so now it's a matter of picking out the function that we want to try and compare this to. And the one I always kind of start with here, personally, I don't even start with the function itself. I start with x minus 0.5. And notice that this would be less than or equal to x. Alright? So moving forward from there, the function that we can kind of play with here is square root of x minus 0.5. That should be less than or equal to the square root of x. Okay? On a side note here, so if you're thinking it's divergent, we got to remember that 1 over the square root of x minus 0.5, that would become greater than or equal to 1 over square root of x. And this integral is divergent. This 1 over square root of x business. And when you think about the next piece, how do we work with the 7 plus sine of x? Well, if you notice, we don't even have to go any further. 7 plus sine of x, the lowest sine can be is negative 1. So this thing has to be greater than or equal to 7 minus 1, which equals 6. But remember, 6 is just, if you don't remember this, we got other issues. But 6 is larger than 1. So 7 plus sine of x is greater than 1. So notice we can create this inequality, 7 plus sine of x over square root of x minus 0.5. And we have this is greater than or equal to 0, right? So since we have a greater than or equal to 0, we have some smaller function. Notice, so we have our inequality that we desired. The integral from 1 to infinity of 1 over square root of x. Now, dx is divergent. Since p equals 1/2 is, and I'm referring to the previous problem, but so that's less than 1. Therefore, our integral from 1 to infinity of 7 plus sine x square root of x minus 0.5 dx is divergent by the comparison theorem. And that's going to be the real trick to all these, finding the appropriate function. So we got two more in terms of what the function is. I'm interested to see number 5. So if you want to post number 5, if you get the function correct, I'll give you extra credit for that as well. But in the meantime, I'll kind of work on number 4. So you can try and take a stab at number 5. And as I said, extra credit if you get it right on that one. So in the first one, though, cosine squared, notice that's always going to be bounded. Since cosine ranges from -1 to 1, cosine squared of x is always less than or equal to 1. In terms of x squared plus 5, we'll go on that side of things. That's going to be our main focal point. X squared plus 5 is greater than or equal to x squared. This probably looks familiar. So 1 over x squared plus 5 is less than or equal to 1 over x squared. And we know that that 1 over x squared plus 5, well, 1 is a bound for cosine squared. So the cosine squared of x over x squared plus 5 has to sit below that. And since we're squaring that top term, that's always going to be positive, so that's non-zero. So we have our inequality, and we know what 1 over x squared does. So we can do 1 to infinity of 1 over x squared dx. And so this makes what? Well, this is a convergent improper integral, since p equals 2 is greater than 1, and the integral from 1 to infinity of cosine squared of x over x squared plus 5 dx is convergent by the comparison theorem. Hopefully I wrote it on the previous one. Should have said by the comparison theorem. Okay, got it on all three of those. Good. So in terms of this next one, we want to try and use the comparison theorem one last time. It looks nasty, actually pretty horrible in terms of what's going on. But so in this case, what I'd recommend, and this takes some practice, so you might see this pull off. Sometimes you'll pick functions, you'll think it's the wrong thing, convergent or divergent, in either direction. If you think it's incorrect, that's okay. If you find that you aren't being able to get the inequality to work or something like that, it might be incorrect and you might need to take a different approach. So don't hesitate to try different things along the way. In this case, it's the denominator that makes this look nasty. So x to the 6 plus 5, what's the one thing that we can compare it to easily? Let's try that first. And I'd say this is going to always be bigger than x to the 6 for on 1 to infinity. I've gotten a little ahead of myself. I should always explain the interval, but I think that's kind of self-explanatory considering the bounds. If not, if you struggle with that, let me know. I'm happy to list that all the time. So, because like technically I can't always say that all these inequalities hold if it's outside of 1 to infinity, but all our integrals have been from 1 to infinity. So in this case, though, if I take first off the square root of both sides, that's not going to change a thing. But actually, it does make life a little easier. This becomes the square root of x to the 6 plus 5 over, well, this part becomes just x cubed, but we need to take the absolute value just in case it was a negative, even though we can actually get rid of it now because it's on the interval 1 to infinity. Okay? So hopefully that's working out so far. So I don't need the absolute value. I'm just trying to get you in the habit of it when you do have those negative bounds. But so now what happens? This is 1 over the square root of x to the 6 plus 5. That has to be less than or equal to 1 over x cubed. Now technically I should have this absolute value. Now multiply both of these by x. Since we're on a 1 to infinity, it's not going to change anything. So we aren't multiplying by a negative, so there's no harm, no foul there. So this is x over, well, when you go absolute value of x cubed, basically this becomes 1 over x squared. Right? And you don't need the absolute value because every square is going to be positive, so we didn't even need to worry about that. So you have this holds. Well, and once again, we're back to that 1 over x squared. So the integral from 1 to infinity of 1 over x squared dx converges. So the integral of x over square root of x to the 6 plus 5 converges by the comparison theorem. Okay. So hopefully that stuff made sense. Oh, yeah, so question. Is there a reason in the first example you put the square root in automatically when you came up with your function? In the first example. In this example you went ahead and squared it after. Say that again. Hold on. So you're referring in the first example with the square root, I'm assuming? So in this example, technically I started with a different line. I went x minus 0.5 is less than or equal to x, and then I put the square root in. So I rather than draw another line, I was running shortened space. That's why I drew it in there. In this example, drawing it all on the same line, I think I might misunderstand your question. Is there a reason in the first example you put the square root in automatically when you came up with your function? Okay. No, I just kind of, I did that first step, the x minus 0.5 is less than or equal to x, and then I took the square root because that doesn't change when we're talking on the interval 1 to infinity. It's not going to make any changes or anything like that. When we go moving forward to this next one, when you see in this case, it's looking at this step right here. We start with x to the 6 and x to the 6 plus 5. Taking a square root of both sides is not going to affect that inequality whatsoever because we're talking positive numbers. Taking a square root of a positive number and the positive numbers are also bigger than 1, that's not going to have an effect in terms of our answer. If we had to worry about the number being less than 1. So, you answered it, just did it on the same line. Okay. Yeah, so yeah, in terms of sometimes I take a shortcut for space reasons. So, but yeah, I'm glad you asked in terms of, and I'm glad that answered the question. Anytime you have stuff like that, just let me know. So, but yeah, hopefully that makes sense in terms of what's going on. Okay, so other ones we kind of dealt with something similar to this. We found the value from 1 to infinity of 1 over x to the p. Notice the difference here. You have from 0 to 1 now. So a little bit different sort of scenario in terms of what's happening. Let me make an aside real quick. So case 1, I guess we'll say. We'll solve this real easy here. If p equals 1, then you get the integral from 0 to 1 of 1 over x dx, and then this equals the limit. Where's the problem point? Well, in this case is 0. So limit as t approaches 0, and then we're approaching it from the right hand side. We have no part from the left. So hopefully that makes sense in terms of what's going on. So we go t to 1 of 1 over x dx, and notice that equals the limit as t approaches 0 from the right once again of just natural log of x evaluated at t and 1. So this equals the limit as t approaches 0 from the right of natural log of 1, which we already found is 0, minus natural log of t, which we'll talk about in just a second. So I'm not sure how much you remember. Oh my god, that was a bad straight line. I promise I've only been drinking tea. So in terms of what happens with the natural log function, you get something that goes like this. Well, if I do natural log of x, I gotta be a little bit more careful. If I do absolute value. Okay, so that's supposed to be symmetric. So this is -1, this is +1. Notice as we approach 0 from the right, this thing equals, so 0 minus, so we approach it from the right, we're going down, down, down to -infinity, so 0 minus -infinity. Okay? So this thing equals +infinity, so it diverges. Okay? So hopefully that makes sense in terms of the natural log case, and pretty much all the natural log cases do similar stuff. So now, moving forward, let's get to the good stuff. Okay. And the good stuff is case 2, if p does not equal 1. We already found what that antiderivative of 1 over x to the p is, so I'm not going to hold us up too much on that. So we're going to take a look at limit as t approaches 0 from the right of t to 1 of 1 over x to the p dx. And just so you can have it as a reference, actually I will go back just so you can see what that antiderivative was. And so notice the bounds are different, but if you look, what was this antiderivative? Well, we had 1 over 1 minus p, and then it's 1 over x to the p minus 1. Okay, so 1 over 1 minus p, and then 1 over x to the p minus 1. So I'll kind of keep that in mind. That equals 1 over 1 minus p, and 1 over x to the p minus 1. I'm going to rewrite that in a certain form this time. Evaluated at t and 1. Okay? So in this case, it might look nice, but notice we're going to have 1 over 1 minus p, and then you have 1 over 1 to the p minus 1, that's still going to be 1, minus 1 over t to the p minus 1. And that might look kind of nasty, right? Because we're taking t to approach 0 from the right. We don't want that to be in the denominator. So another way for us to write it, now here's where we'll look at it the other way. We could write this as a negative in the denominator, so making it t to the negative p plus 1, right? Or t to the 1 minus p, either way. Now, why would we want to do that? Because now, rather than the other time when we wanted it to go in the denominator, now we want it to be in the numerator because we're approaching 0. So what we need, in order for that to stay in the numerator, we need 1 minus p greater than 0. Okay? So if that's to happen, notice we have 1 is greater than p, or you can think of this as p is less than 1, right? Same thing, p less than 1. So what happens then? Well, then this whole thing goes to 0. And so what our integral becomes, our integral from 0 to 1 of 1 over x to the p, notice it equals, well, that's to 0, and then you're left with 1 over 1 minus p. So pretty similar to what happened in the other case. All right, so in general, let's say we had the integral from 0 to 1 of 1 over the cubed root of x to the, so I got to keep it less than 1. So notice that's x to the 2/3. Well, this integral right away, without doing anything, since that's x to the 2/3, that goes 1 over 1 minus 2/3. So that thing should be 1 over 1/3, which is equal to 3. Done. Right? That's the beauty of this once we solve it. Okay. So go ahead and take a shot. Try and make sure that you understand that that equals 3 with those numbers and stuff like that. And hopefully that works out nicely for you. Alright, so try one more with the p business. What's going on here? You have 0 to 1, x to the p, natural log of x dx. So this looks all sorts of nasty at first, but then we can do the whole antiderivative thing once again. X to the p, natural log of x. So now, as long as p doesn't equal -1, and that becomes a different case, but well, I'll discuss that in a second if p equals -1. So if p does not equal -1. So what's going to happen? Well, in that case, we get this integral. We're going to have to use integration by parts. And we don't know the antiderivative of natural log off the top of our head, so we'll call that our u. That means our dv has to be x to the p dx, meaning v equals 1 over p plus 1, x to the p plus 1, and then the du equals 1 over x dx. And if I move too fast with the algebra, just let me know in terms of what's happening. But so integration by parts goes, if you don't remember, that goes uv minus the integral of v du. Okay. So uv, I'm going to actually write that out of order rather than write natural log of x then times 1 over p plus 1. I'm going to try and get the constant in the x term first. 1 over p plus 1, x to the p plus 1, and then natural log of x minus, notice the v du, the 1 over p plus 1 is a constant, so we can pull that out. So it goes 1 over p plus 1, and then it goes the integral of x to the p plus 1 times 1 over x dx. Okay? And to make that a little bit nicer, we can factor out a 1 over p plus 1, and we have, notice this integral, by the way, just becomes x to the p, because this plus 1 will cancel off with that x down below. So we have x to the p plus 1, so natural log of x minus, and we already know that antiderivative because we already had the dv there, so minus another 1 over p plus 1, x to the p plus 1. And I'll put a plus c in there. Okay? So hopefully that made sense on that part. In terms of our integral, where's this thing undefined? Well, you can't plug in 0 into the natural log. So you need the limit as t approaches 0 from the right. Okay? And so in that case, what do we get? Well, we get have 1 over p plus 1. Well, before I get into the antiderivative, let me do this. The integral from t to 1 of x to the p, natural log of x. So this way we can approach that and have it make sense. So now, moving forward from there, this equals, the limit as t approaches 0 from the right. We have a 1 over p plus 1. And now here's where it gets kind of funky. You get x to the p plus 1, natural log of x, minus 1 over p plus 1, x to the p plus 1. Evaluated at t and 1. Okay. Hopefully that makes sense on that part. And so, in terms of where do we go from here, well, oh, and once again I'm doing if p does not equal -1. I'm going to make it as an exercise if p equals -1, because that'll be a slightly different integration by parts. So now moving forward, what do we get? We get the limit as t approaches 0 from the right. this will be t to the p plus 1 natural log of t, which looks like a pain, but we'll be able to take care of that in just a minute, minus the 1, or over p plus 1. I forgot the 1 over p plus 1. Minus 1 over p plus 1, and then it goes t to the p plus 1. Okay? Then, after that, we got to subtract off, and we're going to put in a whole bunch of 1s. Okay, so we have, this would be 1 to the p plus 1 is this 1, times natural log of 1, which is going to be 0, minus 1 over p plus 1 times 1. Okay. So hopefully that works for you thus far. Now moving forward from here, a little bit trickier. Where do we go from here? So in terms of what we have in this part, that goes to 0. And notice, in order for this to be convergent, right here, as t is approaching 0, we need p plus 1 to be greater than 0. Okay, so that means p has to be greater than negative 1. But that doesn't tell us about this just yet. So we need, on this part, we need p to be hopefully greater than negative 1. Let's check. If p is greater than negative 1, notice we can rewrite this as natural log of absolute value of t over 1 over t to the p plus 1. And this is the tricky part. This might not be a limit you remember right away, but limit as t approaches 0 from the right. What's the purpose of that? Well, that gives us negative infinity up top, and 1 over 0 to approach the right, 1 over, and as we approach 0 from the right, that goes to infinity. So this means we can use L'Hopital's rule. So we'll use L'Hopital's, and so that means we get limit as t approaches 0 from the right, and this would become 1 over t. And since that's t to the negative quantity p plus 1, so that's, hold on, I want to take the derivative of this. And we're taking the derivative of this with respect to t, so hopefully we can see this. So that equals, we bring that down, so you get negative p plus 1, t to the negative p plus 1, and then we go minus 1. Well, notice that makes negative, and then it goes minus 1, so that's minus 2. Okay, so I see a, yeah, so L'Hopital's rule, and so the question is, you keep going until it equals 0. Well, that's what we're hoping. We're hoping this thing equals 0. And it won't be a problem, though, actually. It turns out to be pretty nice. So t approaches 0 from the right. So notice we have negative the quantity p plus 1, and another way we can write this is 1 over t to the p plus 2 power, and that looks all sorts of nasty, right? But if you keep that in mind, we're going to show that this whole thing equals 0 in this case, because if you simplify that, the t p plus 2 and the t here, this can be simplified to limit as t approaches 0 from the right of just t, and then p plus 2 minus 1 would become t to the p plus 1. And notice that whole thing equals 0 if p is greater than negative 1. So we found that it equals 0 since p is greater than negative 1. So technically we found our convergent area there. So this whole thing goes to 0 in that case. And what we used is actually the first term, right, where we just use that first piece. And so what we're left with is just, notice we had 1 over p plus 1, and then we have a negative and a negative here. So this whole thing is just 1 over p plus 1, the quantity squared, if p is greater than negative 1. And so that's when the integral converges. And so an exercise for y'all. So I'll erase the bottom. So notice the one case we start with p does not equal -1. If p equals -1, I claim is that 0 to 1 of x to the -1 natural log of x dx diverges. Okay, and so that will also be another eagle egg if you can get that to me by Wednesday. So that would be January 31st. Then if you get it to me by Wednesday, handwritten, you can write it all out, of this integral diverging, showing all the steps, I'll give you an eagle egg for that as well. So moving forward to the next piece, we have these continuous functions, and these things Laplace transforms. What they're Laplace transforms, the big deal about those is when you get to, say, a differential equations, if you ever have to take that course, these turn these nasty integrals and things of that nature into algebra problems. So all you have to do is just add and subtract things, and that's the whole idea of what we want to do. We want to make things as easy as possible, and so the Laplace transforms are the key component to that, and it cuts down on time, and it's used pretty often, like electrical engineering and things like that. It pops up all over the place. So I want to try and illustrate what that is and how we actually go about calculating stuff. So if we have an integral from 0 to infinity of f of t e to the negative st, and we say f of t equals e to the t in that first case, we can find this function in terms of s. And where's the s coming from? Well, the s is going right there in terms of that exponent. So we can have the integral from 0 to infinity of e to the t, and then you have an e to the negative st, right? And so then a dt. An easier way for us to write this and try and solve it, notice we can add that. So we get e to the negative st, right, plus t by adding the exponents. And so you can rewrite that as e to the negative s plus 1 times t. So this thing becomes the limit as, I don't want to use t anymore because we have t's involved here. So let's say limit as y approaches positive infinity of the integral from 0 to y. So we go e to the, and then in this case it's negative s plus 1 times t dt. Okay. So if you're taking a look at these integrals in general, how do we solve that? Well, we're solving in terms of our antiderivatives in terms of t. So if you let u equal negative s plus 1 times t, and that means du equals negative s plus 1, the quantity dt. And so dt happens to be du over negative s plus 1. So this thing equals, and I'll pull the negative 1 over s plus 1 out. Oops, put that in the wrong spot. I need a negative down below. So you have negative s plus 1, and so what happens from here? We get an integral of e to the u du, and so that's 1 over, I'll just rewrite that as 1 minus s, that'll be a little bit easier for us, and then this is e to the u plus some constant c, so this is 1 over 1 minus s, and u was negative s plus 1, so e to the negative s plus 1 times t, and then all that's plus c. Okay, so we have our antiderivative. This thing becomes the limit as y approaches infinity of 1 over 1 minus s, and then e to the negative s plus 1 times t, evaluated at 0 and y. Okay, so moving forward from there, you get limit as y approaches infinity. You can go 1 over 1 minus s, and then this becomes e to the negative s plus 1, and I'll put this in parentheses, negative s plus 1 times y minus e to the 0, because you plug in for the t, you get 0 there. So now what does this become? Well, we want this thing, and so I'll erase the bottom real quick. We need that to be in the denominator. So in order for that to happen, as y goes to infinity, in order for that whole rest of this to go and have a solution, this ties into the domain, we need negative s plus 1 to be less than 0. So that means that s has to be greater than 1. Okay, so there's our domain for our function in terms of s. And so now what happens? Well, we get that this thing equals, moving forward from there, you can now take that limit as this thing goes, and if s is greater than 1, this would go to 0 because it puts it in the denominator. And so we're left with 1 over s, or 1 over 1 minus s, times negative 1, because that's where you have the e to the 0 business, right? So multiply that negative 1 on through in the denominator. Notice you get 1 over s minus a. And you're done. And the beautiful thing here, or not s minus a, I'm sorry, s minus 1. Don't know why I put a. Oh, I know why I put a. I'm thinking in terms of general functions. So this equals 1 over s minus 1. So now, what's the big to-do here? So let's say we had the integral of e to the t times e to the negative 17, or not negative 17, I need that to be positive, 17, oh yeah, no, since it went negative s, negative 17t dt. Notice this is s equals 17. So it's satisfying our domain. So this whole thing equals 1 over 17 minus 1. Right? So this is capital F of 17. And so that's 1 over 16. And I'm done with that integral in a matter of seconds. Right? So as long as I know that, what that's going to behave like, we're good to go. Alright, so these Laplace transforms pop up over and over again. And you can find all sorts of them. In particular, so the Laplace transform of this one, you get f of s equals this integral from 0 to infinity of f of t, which is t, and then you have an e to the negative st dt. Okay, so once again, this is an integration by parts. So you'd say u equal to t, and then that means du equals dt. In that case, dv equals e to the negative st dt. Let me put a dt in there. And that means v would have to equal negative 1 over s times e to the negative st. Okay, so you go u times v, so you get t, oh, let me put negative 1 over s, t e to the negative st, minus v to u, so minus a minus will make a plus 1 over s, and then an integral e to the negative st dt. So this thing becomes, notice you can factor out, well, I won't factor out the 1 over s, even though you can. Negative 1 over s, t e to the negative st, plus 1 over s times, we already know that antiderivative is negative 1 over s again, e to the negative st, and then plus some constant c. So this thing equals negative 1 over s, and notice I can factor that out from both terms. I get t e to the negative st, and then I get plus 1 over s, and then it's, well, e to the negative st plus c. And you might ask why I didn't factor out the e to the negative st in the second term. It's because we're going to need to do something special when we take that limit with the the t. Well, actually, no, we can do that. So in terms of what goes on, we can write this as negative 1 over s e to the negative st, and then we get t plus 1 over s. So we can do that a little bit easier. Alright, so, and plus some constant c. Taking this this good old antiderivative here, so we can first rewrite it, limit as y approaches infinity, 0 to y, oops, and then we have t to the e to the negative st, and that equals the limit as y approaches infinity. Making it just a little bit simpler too, we're going to write that as negative 1 over s. And then for the next piece, we'll write it as t plus 1 over s, and then you have an all over e to the st. Rather than e to the negative st, I'll put it that way. And in that case, evaluated at 0 and y. And why would we do that? Well, in this case, we can kind of simplify things, make things look a little bit nicer for us. So, let's see here. We have negative 1 over s. And then we'll have limit as y approaches infinity. And so it goes y plus 1 over s e to the sy, right? Notice if you plug that in, you get infinity over infinity if sy is greater than 0. Right? And then we could use L'Hopital's rule, and the 1 over s goes to 0, the y goes to 1, and then you're left with some e to the sy in the denominator. So notice the y was going to positive infinity, so we just needed s greater than 0. And now the other piece, the other component that we need is minus. So we get 0 plus 1 over s all over e to the 0. So in the first case, though, if s is greater than 0, this whole thing right here goes to 0. So in terms of what we have, we're left with negative 1 over s minus, or times a minus 1 over s. So notice that equals 1 over s squared, right? So if, once again, we needed s to be greater than 0. Okay? And that's kind of convenient. This is where your homework stopped, but extending further, where does this go? Well, you can actually generalize this to some t to the n. My recommendation would be to look at, first off, let f1 of t equal t squared. And then you'd have, in that case, f of s equals, and you can check this out, 0 to infinity of t squared e to the negative st dt. You could do a similar process. And when you take your integral, you're going to get the first, the previous Laplace transform. And you can kind of reiterate this. So first off, this thing, after all said and done, you do all the work, you're going to get that this is 2 over s cubed. Or what we like to say oftentimes is 2 factorial over s cubed. If you let, let's say f2 of t equal t cubed, then you get f of s equals the integral from 0 to infinity of t cubed e to the negative st dt, and then you can get 3 factorial over s to the 4th, right? And you can keep on doing this, and when you get to some, well, I'll say this is the nth minus 1, well, let's just say f of t, and some t to the n, what you get in that general case is by building this pattern, you get t to the n e to the negative st dt is going to equal, well, what happened? When we had 3, we got 3 factorial on top. When we had 2, we had 2 factorial on top. The previous one, 1 factorial is just 1, so you're going to get n factorial on top. And down below, notice we had n, so when it was 3, it went to 4. When it was 2, it went to 3. So in this case, it'll go to s to the n plus 1 power. So essentially, you get this generalized formula. Well, what's the big deal? Well, when you take an integral of, say, t to the 107th from 0 to infinity of e to the negative, and let's say 18t dt, we can solve that in a mere matter of seconds. So that's going to be 107 factorial over our s value is now 18, so we get 18 to the 108th power. Done. No work, and actually making that calculation is going to be a pain in the butt, right? But it took us a matter of seconds to solve that. So that's the beauty of a lot of these Laplace transforms, what they can do. Alright, so last but certainly not least, I want to touch on error bounds and things like that. So yeah, I see. Wow, that's exactly right. In terms of Laplace transforms, they can do tons of stuff for us if you just learn them. I'd suggest going through, I just kind of breezed through those parts just because I didn't want to get too long. I wanted to get onto the error bounds. But I'd strongly recommend taking a look at those calculations. And if you want to see them again, stop by my office or ask it another time, and I'll create a whole session on them, just on those Laplace transforms. Cut down your time. So in terms of the error bounds, we have one. So the main ones that you're learning are midpoint rule, trapezoidal rule, and Simpson's rule. And each one has an associated error bound. And why do we care about that? Well, so it's nice to go and calculate just willy-nilly, but the biggest thing that we want to know is how much error would be involved and how many sort of parts do we need to break it into in order to get within a certain error. That's the key component that we're gunning for. And so the error estimate in terms of the midpoint rule is this, the absolute value, so you can think of it as a margin of error, is going to be less than or equal to some k times b minus a, that quantity cubed, all over 24n squared, where n is the number of rectangles, b and a are talking about your interval, and then a k is just some number that bounds the absolute value of the second derivative. Okay, so say we had this, and the nice part why I like this integral, the integral from 0 to 1 e to the x squared dx, you're going to probably need a calculator for this one though, just a heads up, if you're trying to actually get the number of rectangles. We could always just leave it as is and say, oh, someone else can figure it out in terms of once they have a calculator. But we'll kind of go through it. In terms of what we're wanting, determine the necessary number of rectangles for the error using the midpoint rule. Not saying that's the best here, but to be less than 0.001 for the integral from 0 to 1 of e to the x squared dx. You cannot solve that using the methods of integration that we've learned thus far. So that's meaning whether it's the trig substitutions, whether you use integration by parts, whether you use u substitutions, or it's not a trig integral obviously, or partial fractions. None of those will actually work. Even your table of integrals won't work. We'll actually get something a little bit later on, but as of right now, the best we can do is just with an estimate. And so say we wanted to find out how many rectangles we need to get within this accuracy. Well, the way to do that is, so we want to look at, solve for n. So first off, we're looking essentially, now notice the error bound is always less than or equal to this value. Right? So if the error bound's less than this, if we set this less than or equal to 0.001, then all of a sudden we got the error bound bounded by 0.001. Okay, so that's what we'll kind of gun for. And notice we can do some solving here. It's not too bad. 24 is a constant. K has to be a non-zero constant because we're talking absolute value. And b minus a, we can solve for that. So for example, n is what we are looking for. In this case, a equals 0 because it's the bottom bound. B equals 1. In k, we need some work. And what we need to do is we need to take f of x equal to e to the x squared. Okay, so that means f prime of x equals 2x e to the x squared. And now here's the tricky part for a lot of people. F double prime, you need to use the product rule. So it goes, when you use the product rule, you get 2 times e to the x squared plus, so it goes 2x times the derivative of e to the x squared, which we know is 2x e to the x squared. Okay. If you don't remember that product rule, just let me know. And so this whole thing becomes, notice we can factor out an e to the x squared. And I know I can factor out a 2, but I want to leave that in there. E to the x squared, and we have a 2 plus a 4x squared. Okay. So what does that mean on this interval? Well, notice on the interval 0 to 1, e to the x squared, that's always positive, and 2 plus 4x squared is always positive. So that means this function is always increasing, or I shouldn't say the function is always increasing. Well, I should take an x derivative, and just to be careful, but I'll let you know, once you take the third derivative, you can see that this function, e to the x squared 2 plus 4x squared, is always increasing over that interval, because you'll have the e to the x squared still involved. It's going to be positive all times. And then you'll have a whole bunch of stuff that's on the interval 0, 1 and a whole bunch of positive numbers. You don't have anything turning negative, essentially. So this function here, the f double prime of x, is actually an increasing function as well. So what that means is we could just plug in the endpoint. So f double prime of x is always going to be less than or equal to, I'm not saying it'll always work out this way, but it's going to be e to the 1 squared times 2 plus 4 times 1 squared, which happens to equal, well, what it's going to be is just 6e. So our k value, and we could choose something larger, but we'll choose it as close as we can, because the closer it is, the closer your bound will be for that n value. So we say 6e. All right, so we got all that business. So now, taking that to finish, I'll move that up here in this little gap here. Notice we get 6e times 1 minus 0 all over 24 n squared, which n is what we're going to solve for, is less than or equal to, think of this as 1 over, that's going to be 1,000. So what we can do to make things simple, n squared is positive, 1,000 is positive, so we can go 1,000 times 6e divided by 24 is less than or equal to n squared. And since we're talking a positive number, granted when you take a square root you get positives and negatives, but negative doesn't make sense when we're talking a number of rectangles. So we can just worry about the positive version. So n has to be greater than or equal to the square root of 1,000 times 6e, well, let me just make this, the 6 and the 24, there's some stuff that cancels right there. So you can write this as e over 4. Now this is where you need a calculator. Well, if you could do it without a calculator, kudos to you, you're awesome. But I'm not that good. So if I hit 1000e, and you can find your e button on your calculator, divided by 4, and you take the square root of that, the number I get here is 26.0686. So remember, n is a number of rectangles. So in this case, so there are some restrictions on Simpson's rule, like in terms of even numbers and odd numbers and things like that. Midpoint, no, there's not really much. So in terms of our needs, we need to round up. So need at least, well, not at least technically, we need 27 rectangles. And you can do similar things with those air bounds. So, I mean, whether it's Simpson's rule, I think Simpson's rule uses the fourth derivative, so you're going to need to take a few more derivatives. Trapezoidal rule, there's some different bounds down below, but it's a second derivative in that case that you're going to use and try and find bounds on that. So hopefully that makes sense on the air bounds and trying to use all that business. So if I don't see any other questions, I hope all worked out, and hopefully this helped you out, and I wish you all the best luck. Just keep on asking questions in the course. That's what I'm looking for. So, okay, have a great night.